So we know what the basic exponential function looks like, right? B to the x, where b is a positive number but not equal to 1. So you have a constant raised to a variable, and the basic one is just b to the x. So I'm going to write the general exponential function. So we'll write f of x equals, and I'm going to start it off like this, a with a sub o, and we usually call that a naught, like N-A-U-G-H-T. So a naught, I'll tell you what it is in a minute, times, and then we'll write our b, but now just not to the x, but b to the kx. And we still have the same restrictions, right? B has to be greater than 0, so that has to be a positive number. All right, that base has to be a positive number, except it can't be 1. Now let's talk about what these other letters are for. We've got an a naught, a sub 0, or a sub o, and we have the k. So what exactly are these? Right? They don't appear in the basic function. This is more general. So when you compare these, it looks like the basic function, we could have a multiplier out here. And then we have a coefficient, a multiplier of the x. So let's see what these are. Here's how I would interpret these. I would interpret these as, say, if I have an application, I'm going to call that the start value, or if you like, the initial value. Let's just talk about that for a minute. Do you remember this form right here? Y equals mx plus b. So this was the slope, and this was the y-intercept. Now the y-intercept, that occurs when x is equal to 0. Now if you think about time, at time 0, the output is this much. So that was the start value. So in a linear relationship, b is the start value. And in an exponential relationship, a naught is your start value. We'll see this in just a second. So when I'm looking at an exponential relationship, this number a naught, that tells me how much output I start with. Now think about this. If x is 0, right, if x is equal to 0, I'll put it in here. If x equals 0, and think about time as time goes by. At time 0, right, when you start your observation, what you have is f of 0 is a naught times b to the k times 0, but this is a naught times k times 0 is 0, and a naught times b to the 0 is 1, so you just get a naught. So what it tells you is, at time 0, the output is a naught. Right, so that's your start value. So if you have some kind of relationship and you come in and start your clock at time 0, how much output do you have already? That much right there. Now, let's just go back here to this linear relationship. So the b, that's the y value. That was the y-intercept. That's how much you start with. That corresponds to our a naught. And what about this k? Well, the k is similar to the m. Now the m, this was the slope, and the slope, that is the rate of change, right? The way y changes with respect to x, or if you want to think of it, is speed, is how fast things are changing in the relationship. Now that corresponds to our k up here. So this k, that's going to be the rate of change, or if you like, you can talk about speed, is how fast the relationship is changing. But instead of speed, I'm going to call this the growth rate. Let's call it the growth rate. In fact, let's just get rid of this stuff right here, although it's true, but it's just easier to think in terms of growth. Now you could have negative growth, which is decay, but we're going to call that k the growth rate. Let's take a look at a few examples and look at what these numbers mean. Let's start with this one here. How about number 1? F of x, the output, is 50 times 3 to the 0.04x, where x is the input. And if we're thinking of the input as time, look what that 50 means. What does that 50 tell you? The 50, that's your start value. That means that you start with 50 units of output. Make sense? What if time is 0, right? You come in, you start your observations, you start the clock, no time has gone by, so x is 0. X is the amount of time that's gone by. You start your clock, no time has gone by, so 0 times 0.04 is 0. 3 to the 0 is 1. 1 times 50 is 50. So when you start your observation, you've already got 50 units of output. Now what about this 0.04? All right, well that is the growth rate. So our growth rate here, I'll make a note, that's our growth rate. And what we're saying is the growth rate is, change it to a percent, 4% per period. Now if we were dealing in say every period is a day, that means that this output, the output would be growing by 4% every day. So we start at 50, the next day it's 4% higher, the next day it's even 4% higher than that, and 4% growth every day. So if I know how to read these functions, I get a lot of information, right? Just by looking at this, I can tell how much I have output, how much output I have to start, and I can tell how fast it's growing. And that is similar to what we did down here in this linear relationship. When I look at the linear relationship, I can tell how much output I had right at the beginning, and I can tell how fast things are changing. Now, before we go any further, do you see what's happening here? Let's just look at this 0.03 here. One more thing about this example. You see this 3 to the 0.04x. We could rewrite that right as 3 to the 0.04 all to the x. And then what do you do with these exponents? Well, what have you got here? This is just some number, so that's like b to the x. So what is this? B is this number right here, which is bigger than 1 to the x. So it's bigger than 1 to the x. So what you're looking at here, and we can see it, this is a growth function. And I'm going to think of it this way. Look at it this way. When you look back at this function, what do you see? I see 50 units of output to start, and then I see a growth function. Now it's growth because I'm thinking two things. First of all, the base is bigger than 1, and the growth rate is positive. So I'm thinking positive, bigger than 1, positive growth. Yeah, this is growth. Look at another example here. F of x equals, let's say we have 25 times, now let's try this one here, 10 to the negative 0.3x. Start value, right here. We start with 25 units of output. Growth rate? Well, the growth rate is negative, but there's negative, what, 30% per time period. So what's happening here now actually? We come in and start our observations. We start with 25 units of output. And then what happens every time period, like every minute or every day or every year, whatever time period is? Well, we're losing 30% of the amount we started with. So we're losing. This is a decay function. So this function here turns out to be a decay function, right? It's decay. Now let's just see how to read it. Here's what I'm looking at. I've got, now this base right here is bigger than 1. So I'm thinking growth. But then look at the growth rate. The growth rate is negative. So this is like negative growth. What's the opposite of growth? The opposite of growth is decay. How about this third example here? F of x is 3 times 4 to the negative 0.26x. So I can see my start value, right? We're starting with 3 units of output. And our growth rate, what about the growth rate? The growth rate is, all right, I'll write growth rate. Well, sort of, if you can read that. The growth rate is what? Negative 26%. So what do you think? Is this a growth function or a decay function? Now, I'm thinking this. I look at the base, first of all. It's bigger than 1, so I'm thinking growth. But then what kind of growth is it? Oh, it's negative growth. Negative growth is decay, right? So when I look at this thing, what I'm reading is this. Negative growth, and that implies that we're looking at a decay function. Here's an interesting one. Look at this. F of x is 0.06 raised to the negative 0.06x. So we know what the start value is. The start value is, can you see it here? What's that multiplier? It's really a 1 times that, right? Look back here to the general function. What do you have? The general function is you have a multiplier times the base. You have something times the base. Now when I look down here, I can see the base is 0.06. So what's the multiplier? It's 1. So my start value is 1. So I start with 1 unit of output here. Now look over here at the growth rate. Here's the growth rate. It's negative. So this is a negative growth rate. Now look at what we have. Look at this function altogether. What do you think? Do you see this as a growth function or a decay function? Well, look at it this way. This base is between 0 and 1, right? It's between 0 and 1, so I'm thinking decay. I'm thinking decay because this is between 0 and 1. Now, what kind of growth rate do you have? You've got negative growth. So what I'm thinking is I've got negative decay, or the opposite of decay, right? I look at the base first, and then I look at this. This is the opposite of decay, or negative decay. Well, the opposite of decay is growth. So this function here is a growth function. And this is a good way to think of these. Come all the way back up here to number 1. All the way back to number 1. So what are you saying? A growth function or a decay function? So I'm thinking this. The base is bigger than 1. This growth rate is positive. So I'm thinking positive growth, right? The growth rate, if b is bigger than 1, you have growth. This is positive. So I'm thinking positive growth. Positive growth, that's growth. So this is a growth function. Come to number 2. This base is bigger than 1, so I'm thinking growth, but then I've got negative growth. So the opposite of growth, right? The opposite of growth. Well, the opposite of growth is decay. Look at this one. Here's the base. It's bigger than 1. So I'm thinking growth. But then I see the growth rate is negative. So I'm thinking negative growth, or the opposite of growth, that's decay. And then I come down and look at this one. The base is between 0 and 1. So I'm thinking decay. But then I've got negative decay. Well, negative decay is the opposite of decay, which is growth.